Okay, so this is the last pre-class reading video of the course. We're just finishing up chapter 11 today. It's all about standing waves, and there's 3 sections here. Section 11.8 is standing waves on strings, and we kind of started this in the pre-class assignment for last class, in which you had that FET animation and you were trying to create a standing wave. But basically what happens is that if you fix a string at 2 points and start shaking it sinusoidally, then what happens is very quickly it sets up what's called a standing wave. And a standing wave has antinodes that vibrate up and down with simple harmonic motion, quite a large amplitude, and it has nodes labeled as ends here, where the string doesn't vibrate at all. And so depending on the frequency, there are certain frequencies where standing waves can exist on a rope for a given speed and for a given length. So, and it's all coming from basically reflections of waves from the ends. But the frequencies, the frequency of the fundamental mode is speed of waves on the string divided by 2L, where L is the length of that string. There it is. So that's 11.10. Equation 11.10 is F1, called the fundamental frequency, is V over 2L. It also has the wavelength, lambda 1, it's just 2L. So a half wavelength is the distance between the ends of the thing. You can use your equation 11.5 to find V, the speed of transverse waves in the string. It's the tension divided by, it's the square root of the tension divided by the mass density of the string, so the mass divided by its length. So you can figure that out. And then if there's a second harmonic, it has double that frequency, and etc. So for standing waves on strings, the frequencies at which the string with fixed ends has standing waves is Fn equals n times V over 2L, where n is an integer, 1, 2, 3, etc. It all corresponds to these different patterns and different number of antinodes. In fact, I think that n, that integer, is actually just the number of antinodes in the pattern that you see. And similarly, the wavelengths are 2L over n, so divided by this integer. So smaller and smaller wavelengths for the more antinodes that there are. And it turns out that a lot of musical instruments are based on standing waves. So a string instrument sets up a standing wave on a string. And you can change the fundamental frequency if you increase the tension, for example, or if you decrease the length by pressing your finger on the fretboard. You can change that fundamental frequency. So there's some examples of that. So the next section is also about standing waves, but now it's about standing waves of sound. So we did standing waves for transverse waves on a string. Now we're doing standing waves for longitudinal waves of sound. And in this case, what you need is a pipe, and they start off with open pipes. But basically, when there's a sound wave inside a pipe, you can set up a standing wave. There's reflections off the ends. And it turns out you can get standing waves at particular frequencies, and it's the exact same equation. Fn equals n times V over 2L, except, so L is now the length of the pipe that's open in both ends, and V is the speed of sound, which is 340 meters per second. Then there's something called a one-end closed pipe, an open closed pipe. In that case, the fundamental frequency is half as much. It's V over 4L. And the other interesting thing is that the frequencies of the open closed pipes are not integer multiples, but instead are odd whole number multiples. So you only get 3 times the fundamental frequency, 5, 7, etc. And there's an example of that. But here it is. So it's Fn is the frequencies of the open closed pipe. It's n times V over 4L, so they're all half as much, but you skip all the even multiples, even harmonics. So standing waves in a pipe is what kind of I guess we call that resonates and amplifies the sound. The original sound vibrations come from some sort of initial oscillations in a wind instrument. So, for example, the reed in a reed instrument, or blowing over the opening of a flute. That's another way of setting up initial vibrations. For brass instruments, the initial oscillations are set up by vibrations of the lips of the player. And the last section is the Doppler effect, but in fact we're going to be skipping that section this semester, unfortunately, just in the interest of doing some course review. So that is it for the pre-class videos. Take care and see you in class.